Okay, so Assalamu alaikum wa rahmatullahi wa barakatuh. Today we are going to continue whatever we have done in the last class, which was related to the bending moment of solid slabs. In the last class, we have learned how to do or how to draw the bending moment for solid slabs, whether they are simple or restrained, and then we have learned how to find the coefficients. After finding the coefficients, we have learned how to find the bending moment, and then we verified our results with an Excel. Today we are going to have 2 or 3 more problems on the bending moment, and then next class we are going to do a full design of a slab. Okay. So this was the problem. Let me just share the screen. So this was the problem. Are you able to see the screen first? Are you able to see the screen?
Yes.
Okay. Okay, so we have solved this problem, if you remember. We have calculated the bending moment for the solid slab, which was case number 1, taking into account the live load, the dead loads, and then we use the equation, as we said, moment is equal to beta multiplied by W multiplied by Lx squared. Okay. Now for today's lecture, we are going to start with another problem. Okay. This is, by the way, this is a screen capture of the Excel that we have used, so you can compare your results for case number 1. Moreover, I'm going to upload for you the Excel sheet, so you can try them yourself and try to verify your results with these Excel. Okay. So today's problem is going to be starting with this particular question. It says for us a slab which is 3 meter into 7 meters. Okay, so we have 3 meter into 7 meter slab, which will be used as part of offices for general use in the Ministry of Education. And then the floor finishes will be 20 mm thick limestone tiles on the top of 13 mm concrete grid. AC ducting and light fittings of 40 kilograms per meter square will be attached to the ceiling. And then characteristic material strength are FCU30, FY460. The design is required to be based on mild environment and fire resistance of 2 hours. And then the slab is resting on two beams on the longer direction or longer side. Calculate the maximum bending moments only. Okay. So the question, once again, the question asks us to calculate the maximum bending moment here according to whatever equation we are having. Okay. Now, as we said, the equation which is used for the bending moment is M equal to beta into W or N multiplied by Lx squared. Okay. So this is the general form of your moment. Now, if we try to analyze if we start analyzing the question, now you can see that the slab is 3 into 7. So if we try to illustrate the slab, we can see that the slab is 3 meter here and 7 meter. And then it says for you here that the slab is resting on 2 beams only, okay, on the longer side. So we have 2 beams here. Okay, so there are 2 beams supporting my slab. Okay. And then some kind of loading has been given. But first, before we proceed with the loading and calculation and everything, we should know whether I need to calculate mx or I need to calculate my. Okay. Or it's only going to be one moment in case of one-way slab. So in case of two-way slab, we used to have mx and my. In case of one-way slab, we have only one moment. So the first thing that we need to do in order to solve these type of questions, we need to calculate, or we need to check whether it's one-way or two-way slab. Once again, why do we that? Why do we do that? We do it for the purpose of checking how many moments to be calculated. Now, if we say we are already having an equation which is Ly over Lx equal in this scenario equals to 7 divided by 3, which is going to be, if we have 7 divided by 3, it shows you
2.
Okay, so it shows you 2.33, which is more than 2. So this turns to be a one-way slab.
One-way slab.
Okay. Now, if it's a one-way slab, then we need to check whether first it is a continuous, whether it's a continuous or it's only one slab here. Now, in the question, as it says, it didn't mention that this slab is a continuous slab. Okay, it didn't mention. It might be a single office. Okay, a single office. So in that scenario, if it's not mentioned, then you need to be taking it as a simply supported piece. Now you can see after we have checked the one-way or two-way scenario, next step is to calculate the bending moment. Now for us to calculate the bending moment diagram, or to calculate the maximum bending moment, we are using an equation which is m equals to beta, which is WL square, and in this case our moment is going to be, since it's simply supported, it's going to be 1 over 8 multiplied by W multiplied by Lx square. Okay. Now already we know what is your Lx. The Lx in this scenario is 3 meters, but we need to calculate our W. Okay, we need to calculate our W. Now, in order for us to calculate the W, we'll come to the weights and loading later on. Okay. In order for us to calculate the W, if you remember in the last class, we have said W is equal to 1.4 dead load plus 1.6 into life load. And we said dead load will be consisting of self weight and the finishes available. Life load will be given as, or either will be given, or you need to verify it from the code. So now if we go and see, if we try to think about it, we have, as we said, we have for dead load, we have two things. One is finishes, and then the second one is whatever we call it as self weight of the slab. Self weight of the slab. Now, do we have, in order for us to calculate the self weight we have learned in last class, that is equal to 24 and 2 dk. Do we have the depth given here in this question? Can you see the depth has been given or not yet?
Given.
How much is the depth in this scenario?
Not given.
Not given.
Not given.
Okay. So
Yes.
in the in the question, the depth has not been given. We need to go and calculate the depth. Okay. So now we need, in order for us to calculate the depth, we need to use a certain equation. Okay. We need to go and calculate a certain equation for the depth. Now, do you remember a certain equation that you have used for calculation of the depth in design of structures 1? Do you remember any equation that you have used for the calculation of the depth? Let me do one thing.
Not sure about it. We found the over depth.
Okay. Just have the question here. I'll make it more organized. Okay. So as we said, the first thing is to check one way. Or two-way slab. That's the first step. So in that scenario, what we said our Ly over Lx. In this scenario, Ly is 7 meters, our Lx is 3 meters. So it's 2.33, which is more than 2. So this turns to be a one-way slab. Okay. Let's have it more organized. Okay. So the next step, let's say check for durability. Okay. Now when it comes to a slab or any element design, we need to know what are the possible failures. Okay, we need to know what are the possible failures for any particular element. So when it comes to a slab, it fails into certain things. Okay, one failure in a slab is bending. Okay, one failure in a slab is bending, where we need to cross-check whether it's going to be whatever we call it as singly reinforced or doubly reinforced. Okay. So one check that you need to do is bending. Another check that you need to do is shear. Whether we are going to have shear reinforcement or there is no shear reinforcement. Okay, and if you remember, for bending, you used to compare between M and MUC, or K and K dash. For V, you used to compare between V and VC. We are going to see all of these in detail later. So once again, the slab can fail either in bending or in shear, or it can fail in deflection. Okay. And in deflection, you used to calculate or you used to check something called allowable span by depth, and then limiting span by depth, or allowable, let's say, and actual. Allowable span by depth, and then let's say actual. Through whatever we call the modification factor. Okay, so once again, bending, shear, deflection. Number 4, slab can fail in area of reinforcement. Do you remember that we have taken something called under reinforced, over reinforced, and balanced section? Do you remember these? Anybody? Anybody can help me here? Do you remember something called under reinforced section, over reinforced section, balanced section? Any person?
Under reinforced section means that the amount of reinforcement is less than the needed amount, and over reinforced is lots of reinforcement, which has no need. It's like extra reinforcement.
Mhm. Okay.
And balance is like the exact amount of weight that is calculated is the same as what the reinforcement can overtake.
Okay. So according to whatever you said now, I'm just recapping. According to whatever you said that for under reinforced we are having lesser than the required, balance the required, and then over is the over required. Okay. So are we designing for balance section or under reinforced or over reinforced? The elements you are designing are using a concept of under reinforced or over reinforced or a balance section.
Under reinforced.
So if you are doing under reinforced, will you do something lesser than the required? Because if you are saying lesser than the required, then your element will fail. Okay. We are designing for under reinforced section, and under reinforced section is not related to having something lesser than the required. In under reinforced section, you are having certain quantity of concrete and certain quantity of steel. In that, you are designing your element in such a way that the stress of steel will reach to the maximum level before the maximum stress of concrete reach its level. We have two materials, one is concrete, one is steel, inside an RCC member. What we are trying to do, we are calculating, we are making sure our equations are ensuring that your stresses of steel will reach to the limit before the concrete. What that will indicate, or what that will show, it will show that you are going to be having cracking. Whenever steel is going to be reaching to its ultimate stress, then you will see that it will crack. Whenever it cracks, or whenever it reaches to the yield point, you will see that cracking is going to be happening, and then it's a good sign for you to see the cracks, since it is going to tell you that there is a problem. Now, if you are talking about over reinforced or a balanced section, in over reinforced, the concrete is going to be failing first. Now, if concrete fails first, then the whole section is going to be going, okay, or is going to be gone, okay, because the majority of the section is actually concrete. Steel cannot take the loading itself. The same thing for the balanced section. In case of balanced section, both of them are going to fail at the same time. So if any failure has happened, you lost both the materials. So in case of over reinforced and balanced section, the material or the element will directly fail. It's a sudden failure. Now when it comes to under reinforced section, since I have designed my equations in such a way that the steel is going to reach to the yielding point first, it will cause cracking to be shown. And whenever cracking are shown, you will know that there is a problem and you will take your precautions. Okay. So here, another check that we need to do is area of reinforcement. If you remember, we had something called AS minimum and AS maximum. And there is something called minimum spacing as well. And there is maximum spacing. These are going to ensure for you as well that you are within the limit of area of reinforcement. That you are not going to go for the over reinforced for the balance section. So once again, we said bending, element can fail in bending, it can fail in shear, it can fail in deflection, it can fail in area of reinforcement, and lastly, it can fail in durability. Now, what do we mean by durability? What do we mean by durability? If you remember, we have talked about durability in the first lecture. We said for us to provide a good durability, we need to supply cover, if you remember. Do you remember when I have discussed the cover?
Yes.
Okay. So what will happen if you are not supplying a good, sufficient cover? What will happen to your reinforcement?
Monitor will affect the reinforcement.
Okay. So one failure might be happening is that the element is having less durability. So what we need to do, we need to check and provide sufficient durability. So once again, these are the 5 checks that we need to have when we are designing a concrete element. If you maintained that your element is safe in these 5, then you can say that your element is safe to take these particular loads. Okay. So now we are going to check. First check normally is going to be for durability. Not all of them are required for this question, but to do a full design, you need to have these 5. Now, the first thing that we are going to do in terms of order, the first thing is to be checked is normally the durability. Okay, so we are going to check the durability. Now, if we see the question, the question says for you that the design is required to be based on mild environment and then fire resistance of 2 hours. Okay, so now you will see that 2 cases or 2 scenarios have been given. One, that I need to protect my reinforcement from the environment, from the exposure. And then we have our element to be protected from fire for 2 hours. Okay, so 2 things need to be taken into account. One is the exposure or the environment. The other one is going to be the fire resistance. So now if we try to go to our extract. So this is your extract. Once again, we are going to go to the table of contents and we are going to search for the cover or durability requirement. So you can see here durability requirement. So you can see for durability requirement, it says for you concrete cover to the reinforcement is going to be different cases here. So we have exposure or environment, and then we have fire. So we have different cases here. We have mild, moderate, severe, very severe, more severe, and aggressive. And you need to understand these. Now the question here has given you already the case, but that will not happen in reality. Okay. So when we talk about mild, we are talking about a regular environment. We are talking about a regular weather. Okay. So if we are designing, for example, a building in Muscat, where the weather is regular, then your building can be designed for mild conditions. Now, if you are having a place where rain is there, now you can see when we talk about environment, we are talking about how severe is the water available in the environment. So if it's only the regular humidity, then we are going to go for mild. If we are having rain, like for example, if you are designing on Salala, you cannot have only mild. So the code says for you, if you are exposed to severe rain, okay, exposed but sheltered as well, protected. So if you are having rain or that particular area where you are designing your building or your element is in a rainy area, then you need to take it into moderate. Now, if there is no protection, or let's keep it simpler, if the rain is too much in that particular area, then you need to design it for severe. Okay. So we have mild, regular, moderate, and severe for rain. We have very severe whenever you are trying to have a building near to the seawater. So if we are designing something near to seawater, then it's going to be very severe. If we are having, for example, a building or a structure which is inside the sea, it should be designed for more severe, or as well the elements which are directly related to the soil, like the foundation, it needs to be designed for more severe cases. And then we have last thing, which is oppressive. Like for example, if you are designing for chemicals, okay, you are designing for chemicals. Now you can see that the liquid effect is going to be higher than the water, and in that case you need to be designing your element for oppressive. So there are different cases for each and every condition of environment you are having. So it starts with a regular environment, and then we go for rain, and then we go near to the sea, and then inside the sea, and then later on severe when it comes to chemicals. So that's the first thing when it comes to the environment. After we understood the cases, we are going to see the tables. Now you can see here we have mild, moderate, severe, very severe, and it goes on. And then here we have lowest grade of concrete as well. Now you can see if your lowest grade of concrete or your concrete grade, for example, is 30, you can see that the cover is higher. Whenever your element or your grade of concrete is stronger, it means that it's going to be harder to penetrate. It's harder for the water to go inside the steel or to reach to the steel. So you can see in C30 the cover is 25 because it's a weaker reinforcement. And then for C35, since it's a stronger, I don't require 25 mm cover. Now we require only 20 mm cover. And it goes on. The same thing here, 35, 30, 25, and 20. Whenever you are going stronger in terms of the capacity of the material, you will see that you don't require the same cover. Now, if we go to our problem, the problem says that we need to design our element for mild environment, and then the grade of concrete is 30. Okay, the grade of concrete is 30. So if we go for 30 and then mild condition, you can see that the cover for the water or environmental suggested by the code is 25. Okay, so we have got here, so we can say, so we have cover for water 25 mm, and then going for the second scenario, which is fire. So if we go to the fire, you can see now fire resistance is there. Now we have a table which is showing for you fire resistance in terms of an hour, in terms of hours, half an hour, 1 hour, 1.5, 2 hours, 3 hours, and then 4 hours. And once again, that depends on the designer opinion on how much he will suggest for that particular building in terms of fire resistance. But that opinion should be logical as well. Like for example, if I'm designing my house, if I'm designing a house for a certain family, then it should be, for example, 1 hour or half an hour. Why is that? Normally, if we are talking about a family who is living in a home, they will easily know where is the exit. Okay. Now, when we talk about the fire resistance, we are talking about the evacuation time, the time required for you to go out in case of any fire. Okay. So for me, if I'm living in a house for a certain period, of course, going out from the house would be something which is easy. I know where are the exits. So I don't require a lot of time for the evacuation. That's why half an hour or 1 hour will be fine. Now, for example, if I'm designing a school, then half an hour is not something which is logical. Since we are having more number of students, since the exits will be a little bit far, so maybe 2 to 3 hours is going to be something which is logical. For example, if we are designing a hospital, in terms of a hospital, we have a lot of patients, a lot of people who require a lot of care to go outside. So half an hour will not be sufficient, but you might be going for 4 hours. Since we are having people who do not know where are the exits, there are people who require a lot of help to go outside. So depending on the nature of the building or the use of the building, you are going to estimate how much is the appropriate fire resistance. Now, in terms of fire resistance here, you can see that in our problem, it has been given that it's going to be 2 hours of fire. Okay, 2 hours of fire. So for 2 hours of fire, and then we are going to go for floor, we have 35 for simply supported, and we have 25 for continuous. So we're going to go for 35, which is a simply supported case. So we can say that the cover for fire is going to be 35 mm. Now, I cannot provide 2 covers, one to protect me from water and another one to protect me from fire. So I'm going to only pick one. And which one that will be? It will be the highest. Now, if I pick the 25 mm for the water. That will protect me from water, but it's not sufficient to protect me from fire, because fire requires 35. I provided only 25. Now, if I provide 35 as my cover, it will protect me from both water and fire. It will be sufficient for both. So always you need to take the higher value. So this is in terms of cover. There is another thing to be taken into account, which is minimum dimension. Okay. Okay. So cover is to protect my steel, and we said steel is going to be weak in terms of water. It will corrode, and then fire, it will melt. Now, what is the meaning of minimum dimension? Minimum dimension is related to the integrity of the whole system, talking about concrete and steel together. Now, we said concrete will not be affected by water, but we said concrete after a long time it might be affected by fire. Okay. After a lot of time, it will be affected by fire. You can see that the cement will be fired, the sand will be fired after a long time. Gravel will not be affected, but the whole concrete is not going to be the same as it used to be. Okay. So once again, cover is to protect your reinforcement. Minimum dimension is to protect the whole element. So now, if we go to our code once again, you will see under fire there is something called minimum dimension. Okay, there is something called minimum dimension, and it's only related to fire because we said water will not be affecting concrete. So to protect the integrity of both elements, we need to see if both will fail in what. So concrete will not fail in water, so I don't need to have a criteria for water for protecting the concrete from water, but I need to have another criteria to protect the concrete from fire, since it will be affected after a certain time. Now, once again, we have fire resistance, and then we have 2 hours of fire. We have beam width, we have rib width, and then minimum thickness of the floor. So it says for you, the minimum allowed thickness that can be used to protect you from 2 hours of fire is going to be 125. So that's the lowest value. Okay, so we are going to go here once again. So the minimum dimension is 125 mm, and this is representing your thickness or depth. I cannot use something lesser than this. Okay, so we check for durability. Now, after we check for durability, we are going to go and calculate loads, because you can see now, after we have done the durability, I cannot have the bending check, the shear check, the deflection check, the area of reinforcement check, unless first we have the loading. So durability comes first. After that, we are going to go to the loading. So now, the third step, let us try to make it a bit more organized. Let's say estimation, calculation of effective depth. Effective depth and overall depth. Okay. Now, what is the difference between estimation and calculation? Anybody? Is there any difference between estimation and calculation? Now, you can see in the previous problem that we have solved, the depth has been given. The overall depth has been given. So if I want to calculate the effective depth, then the effective depth will be calculated directly from the overall depth. Once again, if the depth has been given in the question, then you can go and calculate the other effective depth. The effective depth. Now, for you, if the overall depth has not been given from the beginning, then you need to estimate it. You need to try to come up with a value. Okay, so there is a difference between calculation and estimation. Now, if the depth has been given directly in the question, then you should go for the calculation. You need to calculate the effective depth using the general equation of effective depth, which we are going to take later. Now, if it's not there, you need to estimate. Okay, so I cannot estimate an overall depth or effective depth whenever the depth has been given already. Okay, estimation will only be allowed if the data has not been given for you. Okay, if we see here, now for us, slab will fail majorly in what exactly? Will it fail if we talk about the three main things here? Slab will fail mainly in which one? In bending, or shear, or deflection? What do you think? Since you have already taken design one. Slab will normally fail in bending. Okay. Others? Anybody is having another opinion? Still sleeping, everyone? Okay. Now, have you seen, when you have solved in design of structures one, have you seen any slab which is two-way? I mean, which is doubly reinforced? When you have done your design of structures one, have you seen any slab which is doubly reinforced? Okay, you don't remember. Okay, you don't remember. Now, in slabs, normally we have it to be singly reinforced. In shear as well, you used to have links only in beams. We don't use to have links in slabs. It means that normally we don't have shear in slabs. Okay, it means that if it's singly reinforced, means the loading is not that much, which will cause you a lot of bending or a huge bending. So the bending is less, and then shear is going to be less as well. What about deflection? What about the deflection? Now the slab is a small member or a large member in terms of size?
Large.
Large member. Do you think that it will have less deflection or more deflection?
More.
Okay. Okay. I'll try to clarify. Now let us have bending. Let us have shear. And then we'll have deflection. Now you can see, for example, when we talk about bending, we are having our equation, for example, if it's simple, then WL square over A. Shear is WL over 2. You remember these equations? You remember these equations? Okay. Now, if you see, in both equations, we are having W, right? In both equations for bending moment and shear, we have W. Now you can see, yesterday or last class, we have discussed the unit of loading for a slab. We said the unit of loading is kilonewton per meter square. Do you remember?
Yes.
Okay.
Yes.
Okay. So now let us have three scenarios. I have one slab. Okay, and I have one line, and I have one point. And I told you I need to have 1,000 kilograms. I have a total load of 1,000 kilograms. Okay. Now, which one is going to have less force at a certain area? Let's say, for example, that this is 10, this is 2, and this is 10. Now you can see here, the loading here when it comes to 1,000 kilogram. If I want to if I want to spread this loading into an area, I need to divide it. Okay, so I have 1000 kilometer or kilogram to be divided by an area of 10 into 10, 2 into 10. Do you agree? I have a total loading of 1000 kilogram. That 1000 kilogram is to be divided by an area which is 2 into 10. So now what do I have? I have how many kilograms per meter square? I have around 50. Let us make sure. So 1000 divided by 20. So we have 50 kilograms per meter square. Now what about in terms of a beam? In terms of a beam, it is 1000 kilogram, but now it's divided by a line, and the line is 10. So now it's going to give you 100 kilogram per meter. Now in case of a column, or in case of a point load, you will see that it will not be divided by anything. So it is more concentrated. So it will give you 1000 kilograms directly. Now you can see, if we see the three elements, which is the area, line, and then the point, you will see when it comes to the area, the loading will be lesser in a certain area, in a certain concentrated area. Okay, you will see that your whole load will be distributed along a larger area. Do you agree with me? Do you agree that your load will be distributed into a larger area when it comes to a slab? Okay. Now, if it's into a larger area, it means that your total loading will be lesser. Like the example I have given you, like 50 here, 100 here, and then 1000 here. Now, if your W is less, what will happen to your M?
Will be less.
Will be less. If your W is less, what will happen to your V?
Also less.
Also
less.
Okay, so in this scenario, when we talk about a slab, the bending moment value and the shear force value, you will see that always they are coming to be lesser. They are coming to be very less values. And the reason is that your load is divided into a larger area. If you practiced, if you have seen, you tried anything in terms of projects, if you have seen your previous exams, your previous courses, you will see that the moments in the slabs are lesser than the moments in beams. And that is mainly because of the loading. Okay. So what happens here in this scenario? Our moment is going to be very small. Our V is going to be very small. So if the moment is very small, I don't require to go for a doubly reinforced section. My M is very small already. If my shear or V is very small, then I don't require to go for extra shear reinforcement. So when it comes to slabs, due to the fact that the slab is a large area and my loading is divided into a large area, my moment and shear are very small. And you will see that always your slab is going to be turning to be a singly reinforced section. And then your shear turns to be without, the shear check without, we don't have links or reinforcement in case of a slab because of the less loading in the element. So bending and shear, when it comes to slab, once again, they are not that critical, and the reason that the loading is distributed into a larger area. Now, when it comes to deflection, which one will deflect more, a paper of A4 or a paper of A0? A4, regular A4 paper, A0 اللي هي الوسيلة. Which one, if you are trying to hold the paper from the edges or sides, which one will deflect more, you think?
A0.
A0, right?
Yeah.
You will see
Yes.
because of the large area, of course the slab is going to have a higher weight.
Yeah.
True. So since the slab is a large area, normally it fails in deflection. Why is that? Because it's a large area, it has a very huge self weight. Okay, it has a very huge self-weight. So once again, when it comes to the failures, the major failure which is happening in a slab is not bending, is not shear, is mainly deflection. So that's why when you calculated or when you have done the design in your design of structures one, the main thing that you see your slabs are failing in is in deflection. They will not fail in bending or shear. Okay. So now you have taken one equation in case of in your design of structures one, which is D equals to span divided by modification factor into ratio. Do you remember this equation? Do you remember this equation? Anybody?
Yes, Mister.
Okay. Now, since this is a deflection control, I need to take the deflection more serious than the other failures. So when I go to the VS code, I'm going to go and check. Okay, I'm going to go and check for the deflection. So different things are there. Like we have shear, bending. We have shown it already. There is a deflection. Now in the deflection requirement, you have something called basic span by effective depth ratio. And then you can see that you have different ratios. You have 7 for a cantilever, you have 20 for a simply supported, and then 26 for a continuous element. Okay. Now in this scenario, you can see that we have a basic span by effective depth ratio. So if we try to rewrite this sentence into an equation, okay, we have basic span by effective depth ratio by effective depth is going to equal to a certain ratio. Okay. So once again, if I go and rewrite whatever has been given here, so it says for you a basic span by effective depth will give you a certain ratio. And how much are these ratios? They are 7, 20, and then 26. Okay. So once again, basic span by effective depth will be having a certain ratio. How much are these? Are 7, 20, and 26. So I rewrote my equation in such a way that it's going to be basic span divided by effective depth is equal to ratio. Okay, are we okay till now?
Yes.
Okay. And then you can see here modification of span by effective depth ratio for tension reinforcement. So this is assuming that this is the basic thing without taking into account the reinforcement. Okay. This is the basic if we are talking about a regular concrete without reinforcement. So it says for you, deflection will not only be controlled by the concrete itself, but it will be controlled as well by the reinforcement available. Okay. So it says here, deflection is influenced by the amount of tension reinforcement and its stresses. Then span by effective depth ratio should therefore be modified according to the ultimate design moment and the service stress at the center of the span or at the support in case of a cantilever. The most important thing here it says for you, values of span divided by effective depth ratio should be multiplied by appropriate factor of safety obtained from the following table. Okay. So this is a table where you are going to get your modification factor, if you remember. Now what we have concluded from whatever we have said now, we said there is a span by effective depth ratio, which is for the regular concrete. If steel is there, and steel will always be there, you need to modify it. How to modify it? By multiplying it by a appropriate factor, whatever we call it as a modification factor. Once again, it says for us, you are having a ratio, but this ratio should be multiplied by a modification factor. Now, if we try to rewrite this equation, if we rewrite this particular equation to find the effective depth, then you can see that your effective depth multiplied by ratio multiplied by modification factor is equal to basic span. Now, if we rearrange it for effective depth only, so we can say effective depth, which is known as d small as well, is going to be equal to basic span divided by ratio into modification factor. And this is, on this equation, is the equation which we have came across here. Okay, so this equation actually is available in your BS code, but you should know from where you get it. Another thing, now basic span we should know. Basic span is the length of the, it is the dimension that you are taking into account. And always we say the critical dimension is going to be the shorter dimension. So the basic span you already know. The ratio, depending on the type of element, whether it's simply supported or continuous or cantilever, you will know. Modification factor is the missing one. So how to estimate the modification factor? You used to take that the modification factor is equal to 1.3 or 1.4, right? And from where we have got these things. Now, if you can see in this particular table, we have different FY, FY or service stress, let's say FS. And then if you're FY 250, then this is the typical service stress. Now, in case of FY 460, which is the type of reinforcement we are using, the service stress is normally starting from 307. But that's not our concern. Our concern is that we are using FY 460. Now you can see that there are different values for FY 460. You are having M over BD square, and this is representing for you how heavily is the reinforcement in the element. So here we have almost a very little reinforcement, and then let's say lightly reinforced, medium reinforced, and then it goes moderate reinforcement, and then whenever you are reducing here, you will see that it is going to be heavily reinforced. Now, in this scenario, normally or typical range of M over BD square, the typical range for M over BD square is normally between 0.75 to 1. 0.75 to 1. So now if we see 0.75 to 1, once again, this is a typical range. It means I'm assuming that my range is between 0.75 to 1. Okay, so 0.75 to 1, you can see that our modification factor starts from 1.3 to 1.4. That's why you have been told previously that the modification factor can be taken from 1.3 to 1.4. From where? It came from this particular table. Okay. So now let us take, for example, that our value of modification factor is 1.3. And once again, when I say 1.3 to 1.4 means you can take any values between. 1.3 is correct, 1.4 is correct, 1.35 is correct, and it goes on. Okay. So I'm going to take 1.3. And once again, this is a trial and error. Means we are trying to assume a certain modification factor, and then later on we are calculating the actual one. So now we can see that the effective depth is equal to basic span. Now, if you remember, our slab was 3 meter into 7 meter, and my short span is 3 meter, which is the shorter span, so 3000. Ratio, it was a simply supported. My element is a simply supported, so how much is the ratio? The ratio is 20.
20.
Okay, so we have 20, and then we have 1.3, which is the modification factor. Can you give me the value here? So let's see, 3000 divided by 26. We have around 150. Okay, 115. We are going to round it to the nearest 5. Once again, this is the minimum effective depth. Okay, that's the minimum effective depth. So rather than taking 115, I rounded up to 120. Why we are rounding up? Because we don't want our overall depth to be in terms of decimals. Okay, so 115.38 rounded to the nearest 5. Now after we have got our overall depth, now if we see our section, if we take a section here, okay, you will see that we have two types of reinforcement. In case of one-way slab, okay, we have the blue color, which is representing your main reinforcement. And then we have the green color, which is representing your shrinkage or minimum
Distribution.
or distribution, whatever name you will name it. Minimum, distribution, shrinkage, all of them are fine. Now, according to the definition of effective depth. Now, if we go and see for effective depth, if we want to know what is the effective depth actually, then we can go and see it from here. It says for you the average effective depth for all effective reinforcement passing through a perimeter. Okay. So we are going to go for a center or average. From where? We are going to go from here, from the top till the center, or the average of the reinforcement, or the main reinforcement, of course. This is going to be my D small. Now, what is the remaining thing? If I want to go and take a cross section here, I'm going to zoom it. So first that's D small, and then we have something else called D capital, which is from the beginning to the end. That is the overall depth. So we have overall depth, which is a full thing, and then we have the effective depth, where normally the failures will be happening. Okay, and we'll discuss further later what do you mean where the failures are happening. Now, if we are going to see here, if we are going to see a section or a zoomed section, you can see that we have our bar, and D was till half of the bar. So what is the remaining thing? You can see that the remaining is half of the bar. And then we have a certain area here. Now you can see here that this area is representing the protection before the reinforcement, and this is whatever we call it as our cover. So we have cover, and then we have here half of the bar. Okay. So now if I want to compare between D capital and D small, I would say that my D capital is equal to D small plus the remaining part. So what is the remaining part? The remaining part is first half of the diameter plus the cover. So we are going to go for the cover. D small is 120. Now diameter is not given, so you can assume it. So in this scenario, we are going to assume it as 10. So 10 divided by 2. So once again, I'm assuming the diameter, 10 divided by 2. And then we have the cover. The cover has been taken in the problem, as whatever we have said earlier, is going to be 35 plus 35. So now if you can see, this will be giving you around 160 mm as my overall depth. Okay, this will give you around 160 as my depth. Now after we calculate our depth, we'll be able to calculate our loading. Okay, we will be able to calculate our loading. So we can say now, this is step number, let's call them up. So this is step number 4 now. calculation of loading. So now we are having W. Now W is equal to 1.4 into dead load plus 1.6 into live load. Now 1.4, we said dead load is consisting of the self weight, and we said the self weight is 24. So 24 multiplied by my depth, which is 160. Now first thing that you need to do before going and multiplying, now how much is the minimum depth we said, or thickness? The minimum thickness for 2 hours of fire is 125. How much we have calculated, or how much we have estimated our depth now? We have estimated it as more than 125. So this is going to be safe as well. We require 125, we have used 160. Okay. So this is going to be multiplied by 0.16, since 24 is in kilonewton per meter cube. Now, do we have any finishes in the problem? If we return back to the problem, do we have any finishes mentioned here? Do we have any finishes? Now, once again, you can see we have the floor finishes
we
will
have.
be, okay, so we are having,
Yes.
we have 20 mm thick limestone tiles, and then we have 13 mm concrete scrib, and then we have AC ducting and light fitting. Okay, so we have three things. We have limestone tiles, we have concrete scrib, and then we have AC ducting and light fitting. Okay. Now to illustrate that, now what we are trying to say, we are trying to say that this is my slab. Okay. This slab is having a depth of 160 mm. Okay. Now we said there will be tiles. Okay. There will be tiles on the top of a mortar. So we have mortar here. Mortar, which is cement and sand. Okay. Mortar, cement, sand, and water. They told us that this is going to be 13 mm mortar, and then at the top of the mortar we are having our tiles. So once again we have the slab of 160 mm. At the top of the slab we are having our mortar, and at the top of the mortar we are having limestone tiles. And then it says for us there is light fitting and AC ducting. What is the meaning of AC ducting? Anybody? What is the meaning of AC ducting?
For the pipes of the AC.
Okay, ducting means a pipe. Okay, ducting means a pipe. Okay. So since it's an office, and then they have mentioned for you that there is AC ducting, and then they have mentioned for you that there are light fittings. Okay. So normally, what we are going to have like a false ceiling here, and in the false ceiling we are going to have our pipes, AC pipes or ducting pipes, which are going to be held by the slab. Okay, and then as well in the false ceiling itself you are going to have lights, and these lights are connected eventually to the slab. So now this slab is carrying the mortar, it's carrying the limestone tiles, it's carrying the AC ducting and light fitting. All of these are carried by the slab. Okay, whether they are above or they are below. Now if we see all of these materials or all of these finishes, the three finishes, we need to know from where we are going to calculate them. Now, if we see in the problem, they have given us the thickness of the finishes. Certain thicknesses were given. The only value which has been given for us, okay, which has been, I think I have modified this one, since you don't have the AC ducting and light fittings. Now you can see here that the AC ducting and light fittings have been given to be 40 kg per meter square, since they will vary. Okay. So here, this AC ducting and light fittings have been given for us that they are 40 kg per meter square. Okay. Now we have limestone tiles, and then we have concrete scrid, and then we have the light fittings and AC ducting. Now we understand that the AC ducting is 40 kg. 40 kg. How to convert kg to meter, kg per meter square to kilonewton? We have kg per meter square. How to convert it to kilonewton per meter square?
Multiply into 1000.
We are going to divide by 100, not multiply by anything. Force is equal to mass into gravity. Unit of force is Newton. Unit of mass is kilogram. And then we are multiplying by 10. We don't want Newton in kilogram. We want Newton, and we want kilonewton in kilogram. So to convert from Newton to kilonewton, we need to divide by 1000. And then in order for us to convert from Newton to kilogram, we need to multiply by 10. So we have multiplied by 10, and then we have divided by 1000. Finally, you are going to have division by 100. So to convert from kilogram per meter square to kilonewton per meter square, you need to divide by 100. Okay? So now if it's 40, then it turns to be 0.4. So we have got the first finish, which is the AC ducting and then the light fitting. Remaining limestone tiles and then the scrid. Now from where we are going to get them? We are going to get them from the codes. So we have two codes here. One code is for the live load, one code is for the dead load, if you remember. I have already opened them. One is weight of building and the other one is the live load. They have already been uploaded to you. So this is the weight of building materials. We are going to search for scrid. So you can see scredding, cement and sand, 1, 2, 3. And then it says for you for 12.7 mm thickness, you are having 29.3. Okay, for 12.7 mm thickness, you are having 29.3. Now our problem is 13 mm, is not 12.7. So for us, what we need to do, we'll bring a calculator. We'll have cross multiplication. So 13 divided by 12.7. 13 is the thing that I require. 12.7 is a value available in the code, multiplied by the load given for 12.7. So we have done cross multiplication. Wow. 13 divided by 12.7. So we're having 29.99 or 30. Okay. So the mass per meter square for the scredding is 30 kg. So 30 kg per meter square. We are going to return to our problem. Okay. And then we are going to say now for the scrid. For the scrid, it's going to be 0.3. Since it's 30 divided by 100, it's 0.3. Last thing is limestone tiles. So once again, we are going to go and search for limestone tiles. Limestone. We have limestone. Okay, this is light for the bath stone, if we are talking about bathrooms and hotels. And we have another one, which is medium. So we can take this particular medium one. Or there is a heavy, which is like a marble. Normally we are going to be using the medium limestone. We don't want the heavy tiles to be used. So you can see that the density is 2243. Okay. So we will bring 2243. We will multiply by the thickness of the tiles given in the problems or given in the problem. So we can return and see what is. You can see that it is 20 mm. It is 20 mm thick limestone tiles. Okay. It is very important for you to multiply by the thickness because tiles are coming in different thicknesses, and according to the thickness, you will be having the weight of the tile. Okay. So we are multiplying this one by 0.02, which is 20 mm. So it will give you 44.86, which is approximately 45. Okay, which is approximately 45. And once again, we can have it here as 0.45. 45 divided by 100 is going to be 0.45. So now what do we have? We had two things. One is the self-weight. Another one is the finishes. After we have calculated the dead load, we need to go and calculate our life load. So our life load is 1.6 multiplied. Once again, the life load has not been given. We need to know how to calculate or how to get that particular life load. And once again, if we return back to our problem, you will see that the slab is used for part of offices for general use. Okay? So it is going to be an office for general use. We are going to go to the BS code, which is representing the life load. Okay, so this is the life load BS code. You can see that we have different categories. So we have category number A, or category A, which is domestic and residential activities. We have B, which is offices, which is related to our problem, so offices. And then we have different things here. Okay, so it says for you operation theaters, X-ray rooms, utility rooms, workrooms, or workrooms. And then it says for you offices for general use. Okay? It says for you offices for general use. And this is the loading in case of kilonewton per meter square. And this is in case of concentrated load. We are not using concentrated loads. We are using distributed loads. So the distributed load is 2.5 kilonewton per meter square. You can see from here that this is uniformly distributed. This is concentrated. So our problem represents the offices for 2.5 kilonewton per meter square. So we return back here. We will multiply 1.6 into 2.5. Now, can you get me this W? Can you calculate for me this W and give it to me?
Mister, could you repeat, please, from where you get 0.45, please?
0.45 once again. It is related to limestone. So go and search for limestone. For limestone, there are three options. There is light, which is used normally for bathrooms. You can see it here. Okay. Limestone. And then you have limestone, which is used for medium purposes, like general purposes, like the offices, rooms, and other things. And then you have marble, which is heavy. So some of the clients, they want marble. In that scenario, you need to go and calculate it for a marble or heavy. Now, in general, we don't require it to be heavy. We are designing it to be medium. It's not for a toilet, it's for an office. Now, if you see in your office, this medium limestone is having a density of 2,243. Now, for me to find the weight, we said we are going to multiply by the thickness. So multiply 2,243 by the thickness of the limestone tiles. And the thickness has been specified in the problem to be 20 mm. So if you multiply it, you will get 44 point something. That is rounded to 45, and then from 45 kilogram per meter square to 0.45 kilonewton per meter square. Okay. Now, can anybody tell me the W value? Our W value is 25 point.
10.99.
Everyone is giving me a different answer. Some are 25.
10.99.
Then there is 10.5 and there is 10.9. 10.9?
Yes, Mister.
10.9. 99?
986. So
Okay.
will be, yeah.
Okay, no problem. Okay. So 10.99 kilonewton per meter square. And then we are normally designing our slabs for 1 meter width, strips of 1 meter. So it's going to be 10.99 kilonewton per meter. Okay, so we have got our W. Now after calculation of W, the last step here is to calculate the bending moment. Now what is the equation of bending moment? The equation is M equals to beta multiplied by W multiplied by Lx square. Beta is how much? Since this is simply supported, our beta is equal to 1 over 8. If you remember, moment is equal to W square over 8, which can be written as 1 over 8 W into L square, which is same as beta W Lx square. So our beta is the same as 1 over 8. What is our W? Our W is 10.99. What is our Lx? Our Lx is 3 meter square, or 3 meter and then to be square. Can you give me the value of moment? Can you give me the value of moment?
$12.35. 36.
So 12.36 kilonewton meter per meter width. So this is my M value. Okay. So in the previous classes, on the last class, we have taken a problem on how to calculate the bending moment for a two-way slab. Today we have tried for a one-way slab. There are other two problems which are available in your presentation, and you can try them yourself. Next class we'll start the design problem. Now, before ending this class, I want to highlight two things. One is to verify our results, whatever we have done now with an Excel. Second is to check how normally we find the grades. Before I forget. Now, if you see in this problem, the grade of concrete and grade of steel has been given for you. Okay, the grade of concrete and grade of steel has been given for you. Now, for grade of steel, we have 250, 460, and then 500, if you remember. 250 is no longer available. We have 460, and then we have 500. Okay, we have 460, and then we have 500. You can design either for 460 or you can design for 500. Both of them will give you the same stresses. Okay, both of them are going to give you the same stresses. Whatever is available now in the sites and industry is only 500. Okay, it's not 460. It is going to be 500. But once again, the stresses are going to be the same. How we are going to verify that? If you open our, I didn't upload for you both the BS codes, but this is 2000, or this is 1997. Now you can say, or you can see here that you can see here there is a factor of safety for reinforcement which is 1.05. It means that the code of BS 8110/1997 allowed you for 5% variance. Okay, they said for you 5% variance is allowed. It means whenever I'm going to talk about 460 reinforcement, the code says for you can take 5%. It means if your reinforcement is having a strength of 438 to 460 is still acceptable. You will never get the same stresses all over all over the bars. Once again, the code has given you 5% variance in BS 8110/1997. If you are using 460, then they are giving you 1.05, means 5% variance. So you can see that the code has specified one reinforcement only for you here, which is 460. Once again, 1997 has specified 460, and they said there is an allowance of 5%. The other BS code is the newer version, which is 2004. Okay, which is 2004, and you can see here now in 2004 version, there will not be any 460 reinforcement. And you can see now that the reinforcement factor of safety, instead of being 1.05, now it is becoming 1.15. Means rather than having 5% variance, now they are having 15% allowable variance. Okay, and the grade, you can see that the grade now, instead of being 460, now it is being 500. Now, the first one, if you are using 460, you are allowed to go for 438. If you are using 500 and we are dividing by 15%, then you are going to be allowed up to 434. So whether you have designed for 460 or 500, both of them are going to be okay as long as you are using the correct factor of safety. So it says for you here a note, if you see, it says note number 1, where grade 460 deformed bars are used in design, a partial factor of safety of 1.05 may be used. So once again, if 500, the factor of safety is going to be 1.15. If it's 460, then it's going to be 1.05. Using any of them will be fine as long as the effective stresses are almost similar. One is 434, another one is 438. Now going for another BS, which will show you the grade of concrete, and I don't think I have uploaded this one for you, or it might be uploaded. You need to cross-check. Okay. Which is guide for specifying concrete. Now you can see that there will be a table for you, which will show you which grade of concrete will be used for which purpose exactly. And this is going to be your table. Okay, this is going to be your table. Now you can see, if you are talking about a mild condition, if you are designing a building for mild condition, and it's a reinforced case, then you can see that the minimum to be used is C30. If it's a moderate and then reinforced, then the minimum to be used is C35. If it's severe and then reinforced, you can use C40. Very severe, for whatever type of reinforcement, it goes C40. Okay. And then for most severe, you need to use 50. Oppressive minimum is C45. Okay. Now the last thing, so once again, this will help you. This will help you in determining which grade of concrete is going to be good if you are, okay, if you don't know, if you didn't get the values of grade of concrete. The last thing that we are going to do is to cross-check our results, as we said. Okay. To go for Excel, I'm going to upload for you the Excel. Just remind me later. So we're going to go for one-way slab. Okay. Now just concentrate here, and then we are going to compare it with our result. Now here it says for you supports from grade A to grade F. You can see in the diagram it's grade A to grade F. It does not really matter. This is only numbering, but if you want to change it, you can change it. So A to B. End supports are simple or continuous. We said since there is no continuity, it does not, it has not been mentioned, and this should be taken as simple. Now you can see if we zoomed in, you can see the moment at the end supports are acting to be simple. If there is continuity at the end support, you will see there will be a small value of moment here. Okay. So this is going to be kept as simple. Grade of concrete is 460. Factor of safety 1.05 as we said for the steel if it's 460. Grade is 35. For our case it was 30. 24 was the density of concrete. Number of spans, we don't have 3 spans, we have only 1 span. Now what is the meaning of maximum span? If you have 3 spans, one is for example 7, another one is 7.2, another one is 7.1, then you need to take the maximum of the 3. Now in case of our problem, you have only 1 span, and then the maximum span, which is the short in this scenario, is 3 meters. The thickness that we have taken is 160. The cover is 35. Now how much is the total additional finishes that we had? So if we try to go and check how much is the finishes in our scenario, those who are having a class, they may leave. If you don't have the class, then sit. Okay. So you can see that the finishes in this scenario is 0.4 plus 0.3 plus 0.45. These are the finishes for us. So we are talking about 0.4 plus 0.3 plus 0.45. So it is 1.15. So 1.15. The imposed load is 2.5. You can see now that your ultimate design load, as we have got it here, we have got our design load to be 10.99 if you remember, and we have got it here to be 10.99. How much is the coefficient? You can see the coefficient for the span. For the support, the coefficient is 0. We don't have a coefficient because the bending moment is 0 in the envelope. For the span, once again, if you remember, support is representing a negative moment, span is representing positive moment. In the negative, we don't have we don't have a negative bending moment, so that's why the beta is 0. For the span, we have it as 1/8. So if we go and divide 1/8 using the calculator, then 1/8 is going to give you 0.125. So 0.125 is your coefficient here. Now if you are using 0.125 and you are using the other load, and if you are using your W and everything, you can see that approximately your moment is going to be 12.4. So we have the coefficient and we have the moment. Doing that, we have finished today's session. If you have any question, then you are free to ask. If you don't have any question, then you are free to leave as well.